Statistics for hackers. I've noticed this has caused a little bit of confusion when I've told people about this, because people think of hacker as a person trying to steal your grandma's bank password or something like that. But I'm not using hacker in that sort of sense. I'm using hacker in the sense of probably what a lot of you are in this room, someone whose natural approach to solving problems includes writing code or understanding the world through writing code. And what I've found, it's really interesting, is that statistics is hard, but if you apply some of those skills that each of you have in this room and use those programming skills, the statistics can be easy, or at least much easier. And the trick in statistics really comes down to, well, first I should say my thesis for today is that if you can write a for loop, you can do statistics, and I want to come back to that later. But what statistics really comes down to is asking the right question about your data. And when I work with students or I work with other folks who are trying to learn how to apply statistics well, it comes down to this, to asking this right question. I came across this excellent Dr. Seuss quote a little while ago. He said, "Sometimes the questions are complicated and the answers are simple." And I think this encapsulates the field of statistics. The hard part is asking the questions correctly. And once you've figured out how to ask those questions well, the answers sort of come on their own. So as with any statistics talk or lecture or course, we always like to start with a warm-up. And the warm-up usually involves flipping a coin because it's something that we can all wrap our minds around. So let's think about flipping a coin. Let's say you toss a coin 30 times and you see that it lands heads 22 times. And the question you want to answer is this a fair coin? And now you could have an argument about this. You might say, a fair coin should show 15 or so heads, so this coin's probably not fair, right? But then your friend comes along and says, but even a fair coin could show 22 heads every once in a while. So how do you answer this question? This person on the left saying the fair coin should show 15 heads, we'll call them the advocate, and on the right, this person saying, it could be a fair coin and just show this by accident, we'll call them the skeptic. And basically, the way we proceed here in statistics is to assume in this sort of test is to assume the skeptic is correct. We're going to test what's called the null hypothesis. And we'll ask, what is the probability of a fair coin showing 22 heads just by chance? And so going back to your undergrad or your high school days, you probably learned about the probability of a coin toss is 50%. And the probability of two heads in a row would be 50% squared, so you square 1/2. The probability of two heads followed by a tail would be 50% to the 3, 50% cubed. But then if you're talking about like two heads and a tail in any order, you have to multiply that by the number of possibilities, the number of arrangements, and then eventually from this simple thought process, you end up with a formula that looks something like this. It's the number of arrangements of your heads and tails times the probability of heads to the end times the probability of tails to the end, right? And this is a nice thing. This is called the binomial distribution. And if you plot it out, you see that this gives you a plot of the number of heads you can get as, it's a histogram of the number of heads you get in 20 tosses, or in 30 tosses. And what we can look at here is where our 22 hits right there, and ask, what percentage of these tosses would be that big or bigger? And we get here for the binomial distribution that it's 0.8%. Right? And this actually, if you've heard of these p-value things, this is actually a p-value. We have a p of 0.008 for the data that we've looked at. That says that assuming the null hypothesis is true, assuming there's no effect that we're interested in, the probability of getting our data just by chance is 0.8%. And we can say this is less than 0.05, which is the arbitrary bound that someone long ago decided was the right bound to set, and therefore our coin is not a fair coin. Now, this is nice, and this works for a lot of people, but I find that many people who think in code who think about the world procedurally from the standpoint of writing Python code, there are other approaches that might be more helpful. So for example, why deal with all that binomial distribution thing when you can just simulate it, right? We can do a loop of 100,000. We can do a loop of 100,000 repetitions. We can draw a random integer, 0 or 1. We can ask what the sum is, and if it's greater than or equal to 22, we add 1 to the result, and we find that 0.008% of, or 0.8% of the time, 0.008, we get this result of 22 heads or more, right? So we've just done in 5 lines of Python code what we did previously in a few slides of mathematics. And the point I want to make here is that you all have a way of looking at the world as hackers, right? And you can express some of these statistical ideas in this language that makes intuitive sense to you. The other way works well, right? The other way works as well, but for many people who think about the world in code, I think this is a really good way to solve this problem. All right, so in general, computing the sampling distribution, that's this binomial curve that I showed you, is a difficult thing to do. But also, in general, simulating the sampling distribution can be very easy. So what I want to do today is I want to show you a few recipes for doing this sort of simulation of the sampling distribution, so you can answer statistical questions appealing to the types of coding intuition that you have. So this first one, direct simulation we just saw, that works well when you have some a priori model of the world, like you know that a coin toss is going to land 50% of the time, and you can simulate that. But even in cases, as we'll see, even in cases where you can't get an a priori estimate of what the outcome will be, we can still do some sampling approaches. So the next one I want to talk to you about is shuffling. And sticking with the Dr. Seuss theme, I don't know, does anyone know who these guys are right here? These are one of my favorite Dr. Seuss stories, the Sneetches. So the Sneetches were this group of creatures, and half of them or so had stars on their bellies, and the other halves didn't. And you know, over time, those with stars on their bellies started to think they were pretty special and lorded over the rest of those Sneetches without stars upon theirs, right? So let's say you are a researcher and you want to go in and answer whether the star-bellied Sneetches really are better than those without stars upon theirs. You might go in and administer some sort of test. Right, so here's a distribution of test scores you give to the Sneetches out of 100 points. And the Sneetches with stars have a certain number, without stars have a certain number. You compute the means of those, and you find that the star-bellied Sneetches have a 73.5% average, and the non-star Sneetches have a 66.9 average. So obviously, 73 is higher than 66, but the question you should be asking is this significant? Could it just happen by chance, right? And I want to say this section that I'm going through here is drawn from an excellent talk by John Rouser that he gave a couple years ago at an O'Reilly conference. So he didn't do the Sneetches, but he did something very similar. So is this significant? And you can do this the classical way. If you go back to your Stats 101 and kind of read the table of contents, you'll remember that there's this thing called a t-test. And what you do is you subtract the means and then you divide by some weighted sum of the standard deviations. So we can do that. We can plug in our numbers and we get 0.93, right? All right, so what does this mean? You go read a little further in your Stats 101 text and you see that this t statistic should be distributed this way, right? And that upside down L shape there is a gamma function, and the little V-shaped thing, that's a Greek letter nu, which means degrees of freedom. And you scratch your head and you try to remember what degrees of freedom are, and you go to Wikipedia and it says the number of independent ways by which a dynamic system can move without violating any constraint imposed on it, and you're like, okay. But then you dig a little further, and down the Wikipedia page they say that this Welch-Satterthwaite equation can get you there. So you know how to plug numbers into a formula, and you get 10.7. So that's your degrees of freedom. And then you go to a chart like this, and you look up 11-ish degrees of freedom for a 0.05, and you find that the t statistic is 1.79, and you have to ask if your t value is greater than that. And remember, we computed a t value way back. It was like 0.9, right? And this is not true, so the difference of 6.6 is not significant at the p equals 0.05 level, right? Excellent, and you sit back and you're like, I did it. So the problem here is we've entirely lost track of what question we're answering, right? I know there are probably a few statisticians in this room for whom that logic makes sense and helps you understand the problem. I'm not one of them. I don't know, you may not be one of them either. But so what we can do, some people might say, well, why are you going through all that mumbo jumbo when you can just do this? You just import t-test in from stats models and plug in the right, form of the variance and the right form of everything else. And, you get out a p-value, but again, this might be the right level of abstraction for some people. It's not the right level of abstraction for me, and I'd guess for a lot of folks in this room, this is not a helpful level of abstraction for writing the question. Because, the problem is, what question is this answering? If you're 4 years into a statistics degree, you might be able to answer that off the tip of your tongue, but I certainly can't right now. So stepping back, we go back to this. This is the real key of this problem, this sampling distribution, this student's t distribution. And it's very similar to what we did before with the binomial distribution, where we're asking how often do we get 22 heads with a fair coin. Here what we're doing is we're drawing a different type of distribution, and we're asking for the cutoff and trying to integrate everything above the cutoff. So why don't we use a sampling method instead, something that you and I can wrap our minds around? Well, the problem is, unlike coin flipping, we don't have a theoretical model. We can't simulate a sneetch, right? All we have are these test scores. So we need some way for those test scores to be the simulation themselves. And what we can do in this situation is something called shuffling. So the idea here with the shuffling is that we're going to simulate the distribution of possible test scores by shuffling these labels around. And the motivation is that in the null hypothesis, if star-bellied sneetches and regular sneetches are really the same, it shouldn't matter what the labels of these numbers are. So we can label them however we want. So this is what we do. We shuffle the labels. We've kept the numbers in the same place and just shuffled around the red and green squares. We rearrange them, take the mean and the difference, and we can plot it on our little graph there. We got a difference of 4.8. Then we do it again. We shuffle the samples, we rearrange, and we plot a mean. We shuffle the samples, we rearrange, we plot the means. Shuffle the samples, and in this way we can build up this sort of sampled proxy to the real sampling distribution. And we get an idea there of, in a very intuitive manner, of what we can expect these differences in test scores to be. And of course, we draw the line where our measured data lies at around 6, and we compute that something like 16% of samples show a score difference greater than 6. So if you're keeping track, this 0.16 is not less than 0.05, right? So in the classical statistical sense of looking for p of 0.05, we're going to say that this is not significant. So, you go in and you perform this study, and there's hugs all around. All the sneetchers are reunited with their long-lost brothers and sisters, and you've done your good in the world. But the key is that this shuffling approach works when the null hypothesis assumes that the two groups are entirely equivalent. So I'm sure you can imagine situations where this comes up. The classical thing is testing whether a drug works or doesn't. You look at the drug's effects, you look at the placebo effects, and you can do these shuffling things to figure out whether the drug is effective. I should say a little caveat, like all methods, this is only going to work if your samples are representative. If you have a data gathering problem, that's something completely different. And you also need care for independent trials. Like if you're let's say you're measuring the different test scores of the same sneetch over and over, you might expect them to improve with time. So there's sort of a dependence there of the data on previous data. And in that case, you have to be a little more careful with shuffling. If you want to read more about this, there's this Simon's Resampling the New Statistics. It's a book that you can go and look into that kind of goes into this in a little more detail. But anyway, so shuffling is a nice way to use this sampling approach when you don't actually have an a priori model of the data that you're looking at. Another very similar a similar approach is something known as bootstrapping, and that's what I'm going to talk about next. So if you remember your Dr. Seuss, there was this king of the turtle pond named Yertle. And Yertle the turtle wanted to be the most powerful, tallest, richest turtle in the world. So he decided to get on the back of his fellow turtles and make them stack higher and higher and stand on the back so he could be the tallest turtle in the world. Now, you as a turtle researcher go out to this pond and you're observing these every day and you see that, Yertle has a distribution of turtle heights that he gets to each day. And you want to know, in the long run, if you were to observe Yertle for an infinite amount of time, what would be the average height of turtles that he gets to? And what would be the spread of that? How can you characterize this distribution of Yertle's turtle heights? And so one way we can address this is to use the classic method, which is to compute the sample mean, and you've probably seen things like this before. You can compute the standard error of the mean, and you get some numbers, and you find that it's 28.9 plus or minus 3. And again, this works and is fairly intuitive for many people, but I imagine it's probably not intuitive for a lot of folks in this room. In particular, you may not know what assumptions go into these formula that you're using. And you might wonder, can we use some sort of sampling approach instead where we can wrap our mind around what's going on? And like before, we don't have a generating model. And unlike before, we're not comparing two different groups, so we can't just do the shuffling approach. But there is this interesting solution called bootstrap resampling. And what bootstrap resampling is you take this data and you basically treat the data as a measurement of its own distribution. And what that looks like in practice is you sample from this data set with replacement to generate new samples. So we're going to draw random numbers from this data set, and you'll see already that there's some repeats. We've hit 41 twice. Right? That's what you want to happen in bootstrap resampling. You're resampling with replacement. And you continue on, and you get some other repeats in there, and you end up with a subsample or a resampled version of your data that has a mean of 31.05. All right, so we can repeat this several thousand times, and we end up with a distribution of these mean values. And it turns out that almost magically, this distribution is very close to the analytic result that we computed earlier. And we can do this as a simple for loop, right? We go for I in range 10,000. We pick 20 random points from the sample. This is a way to do it using the NumPy package. And we can say that the mean is, the ith mean is the mean of the sample. And then we look at the mean of all the means and the standard deviation of all the means, and we find something that describes our data. Now, this is a little bit simplistic, but the nice thing about bootstrapping is you can apply it to even more complicated statistics. Like, let's say we go out and we measure not only the height of Yertle's towers, but we also measure the wind speed. And we want to know we want to know how the wind speed relates to the tower height. And we can plot this line on the data, and we can measure the slope and intercept. And it turns out if you do the bootstrap resampling here and you compute the slope and intercept on the resampled data, you get a nice estimate of what that confidence interval might be. So this gives us a general idea of what range of slopes and intercepts we can expect from the small sample that we've looked at. And the cool thing about bootstrapping is that it's actually really, really well studied in the statistics community. I don't want to give the impression that I'm giving you like these recipes that statisticians don't know about. They know about all of this stuff. And bootstrapping in particular is something that's been studied for a long, long time within the statistics community. There are a couple caveats to it that you can read in other places. For example, it doesn't work very well for rank-based statistics. Like if you do the bootstrap of the maximum value, it's not going to give you very good results. It works poorly if you have very few samples. And there are rules of thumb that you can read about in different books about how to apply this if you're gonna really dig into this stuff. And as with the other stuff, as the previous ones, I want to warn you to be careful about selection of biases in your data and non-independent data and things like this. You have to think about it a little bit. But the point is that you have this procedure whereby you can reason through what you're doing to your data and wrap your mind around what the answer is saying. And you can keep the question in mind the whole time that you're writing code. Now, the last recipe for hacking statistics that I really like is cross-validation. And this is something, if any of you have been working in machine learning, you'll be familiar with cross-validation. Basically, cross-validation is a way to determine how well a model is fitting data when you don't have some a priori description of the data. You know, statisticians have worked long and hard to learn how well a line fits data, right? And lines are relatively simple, and you can even bring that along to even more complicated models. But when you start talking about something like a neural net with 16 hidden layers, there's no statistician in the world that can write out the analytic statistics of how that model fits the data. I know someone's going to raise their hand and say, but I did that. If you've done that, tell me. I'd be interested to hear about it. So cross-validation is interesting. And I don't know if any of you have read the Lorax. The book is way better than the movie, by the way. You know, the Lorax is about this faceless beast who goes out into the truffle tree forest and starts making thneeds. And thneeds are, of course, find somethings that all people need. And the Lorax gets rather angry. But let's say you are a data scientist who is hired by Onceler Industries, and Onceler Industries wants you to project thneed sales so that you can help them more efficiently, you know, do their business and hack the truffle tree forest to bits. And you notice, combing through their data, that there seems to be this relationship between temperature and thneed sales, right? And now that's an interesting relationship, and you'd like to predict, based on the temperature, what you think the thneed sales are going to be for any given day, right? So the question is, what model better fits the data? You might have a linear model, this blue line, or you might have a quadratic model, this red line. And both of those by eye sort of seem plausible. But how do you choose which is the better model for actually fitting your data? And you might think, you know, I'll just measure how close the points are to each of those models, right? You compute the root mean square error about the model, and you find that for the blue points it's 63, and for the red points it's 51. But this is something you have to be careful about. The red model is more complicated, and a more complicated model will nearly always fit the data better. Right? If we start doing, instead of a linear model or a quadratic model, or if we do a cubic or a quartic or an even higher model, as we add more terms to that equation, the RMS error gets better and better and better forever, basically, until we have as many terms as we have data points, and then you're fitting the data perfectly. And these higher order models actually look pretty silly, right? If you were going to use this blue line here to predict thneed sales, and you say that at, what am I looking at here? At 20 degrees, you have 0, because that's what the model says. This is a silly model. You don't want to use that one to project your thneed sales. So, you know, statistics has this figured out. What we can do with these sorts of models is we can look it up in the book, and we see that the difference in mean squared errors follows a chi-squared distribution. You can estimate the degrees of freedom, because these are nested models, and you can get these degrees of freedom. And you start plugging in your numbers, and pretty soon you're in the same situation as before. You're thinking, what question were we trying to answer? And one way that I find that I can keep my eye on that question a little more is by doing this cross-validation approach. So what we do in cross-validation is we take the data set and we essentially split it randomly and separate those two parts. And then for each of those sections of the data, we fit our best model. And once we have those best model fits, we then flip-flop the data. And we ask, how well does the red model fit the blue data? And how well does the blue model fit the red data? And this will protect against what's known as overfitting, right? If we have a model that's really drawn to that top left point and really highly influenced by that top left point, then testing the model on a data set that doesn't include that top left point is a better and more robust way to see how well the model is doing. All right, so then once we've done that, we can compute the RMS error for each model. And we repeat this for as long as we have patience to repeat. Fortunately, you can write a for loop, and you can do this as many times as you want in basically a split second. And then we can compare this cross-validated root mean square. So here, this blue curve is what we saw before. As we make the model more complex, it just fits the data better and better and better. But the red curve is the cross-validated error. We're controlling for this overfitting phenomenon. And as we make the model more complex, it hits a minimum where it fits the data well. And then we go on, and we're basically to the point where the model is influenced by the noise in the data more than the data itself. So doing that, we can fit this second-order model to our data, and we can be sure that we have a solid model for the data that we're looking at. It's the one that minimizes the cross-validated error. And then, of course, we've done our job, and now Onceler Industries can go on and take over the world and ship their needs to the south, the east, and the west, and the north. Maybe I should have used a different example. Anyway, so cross-validation. This was known as a two-fold cross-validation. It's because we split the data set into two folds, and then we fit across each of those. There's also different ones. There's things like k-fold cross-validation, where you split the data into k different sets, and you fit on the first. Let's say you split into 10 sets, and you fit on 9 and then test with 1, and then you shuffle them again and fit on 9 and test with 1. There are other cross-validation routines that we can use, and if you look in the scikit-learn package documentation, there's a pretty good description of how to use those and why you might use one over another. I mentioned this before, but cross-validation is really the go-to method for machine learning. And this is because often in machine learning, we're working with models that you can't really do the analytic statistical distribution of the results. It's not like fitting a line to data where you can write down the sampling distribution. If you're doing something like a random forest or a neural net, it's not something that you can compute analytically very easily. And then again, I want to put in the caveats about selection bias and data independence and things like this. So these were the 4 hacking statistics recipes that I wanted to present to you guys. Number 1, the direct simulation. This is where you have an a priori model of your data generation process, and you can actually simulate the whole thing end to end. There's shuffling, where you're trying to decide whether one group is different than another group, and you can shuffle the results to generate that sampling distribution or to mimic the sampling distribution. You can do bootstrapping, where you're drawing with replacement and computing a statistic, computing a distribution of those statistics. And then cross-validation for comparing models, where you don't have an a priori statistical way of looking at those model comparisons. Now, I should just do one aside. I think direct simulation out of all of these is probably the most appealing one. And you'd be surprised how far you can take direct simulation. Like, for example, in astronomy, there's this project called the Large Synoptic Survey Telescope. And one thing that they're doing with that, essentially this telescope is going to start in a few years, and it's going to take an image of the entire night sky a couple times a week over the course of 10 years and give you huge, huge amounts of data. And we as astronomers are going to want to ask statistical questions about this data. And one thing that the group at University of Washington is doing is they're bringing this direct simulation approach almost to its logical end, and they're simulating from the ground up the entire survey, from the photons leaving the stars, going through the atmosphere, going through the telescope optics, landing on the CCD, displacing an electron, the electron going across to the detector, and basically their goal is to be able to apply this direct simulation method to something that's extremely, extremely complicated. So if you have the computational power, you can really do some interesting things with this type of sampling. So anyway, to wrap up, I just want to tell you that sampling methods I want to leave you with this. Sampling methods allow you to use these intuitive computational approaches in place of often non-intuitive statistical rules. And I do want to hedge a little bit before, because I've gotten in trouble for saying things a little too strongly. I'm not saying that classical statistics is wrong, or that it produces bad results, or even that it's a bad way to look at the world. What I'm saying is that I think for a lot of people in this room, the computational approaches will be more intuitive and will allow you to keep the question that you're answering in your mind while you're working with your data. And that, in statistics, is the most important thing, that you keep this question in your mind, because sometimes the questions are complicated and the answers are simple. So a couple things I didn't have time for. I actually talked fast because I would have had time for some of these. But Bayesian methods are a really interesting way to move forward. There's a lot of sampling that goes on in Bayesian methods. So one thing you can look at for this, you might look at Bayesian Methods for Hackers by Cam Davidson-Pillon. It's a kind of all-online book that he wrote several years ago that's pretty good. This idea of selection bias, of worrying about how your data is gathered and whether you're really looking at the data set you think you're looking at. There's a phenomenal talk from last summer by Chris Fonesbeck, who's a professor out in Nashville, called Statistical Thinking for Data Science. You can find the video of that talk online, and I'd highly recommend it. And then detailed considerations of these sampling, shuffling, and bootstrapping approaches. There are a couple books out there that are interesting. I'd recommend taking a look at Statistics is Easy by Shasha and Wilson, and also Resampling the New Statistics by Julian Simon. And there are excellent ways to dig into a little more of the meat of these approaches, because there are some subtleties that you have to worry about. Okay, and with that, I'm finished. If you want to look at these slides online, I just tweeted the link, and I'm at JakeVDP right there. So thanks very much. It's a pleasure to be here, and we'll have some questions.
Yeah, we have time for some questions. If you could please queue up at the microphones, and please remember to keep your questions a question. Thank you.
Can I ask now, or do I have to wait?
Yeah, go ahead.
Okay. Sorry. Okay, so when you're getting sort of a new sample that looks like the sample you already have, is it convenient to use something like importance sampling, where you don't need to know the exact distribution that the thing is coming from? You have another distribution that kind of looks like it, and you know how to sort of apply a correction factor, or like a weighting factor. Is that useful for making it easier to kind of see how well your model's doing?
Yeah, that's a good question. The question was about importance sampling. So you're essentially using other information that you have in order to drive the samples. And yeah, that can be useful. I think it's a more advanced technique, and I'd be sure to read up and make sure you're doing it correctly. I don't think I have much more to say than that.
Thank you for your talk, Jake. It's an approach that very much speaks to how I think, I guess. And so I'm wondering, when doesn't it work? Like, what should I be on the lookout for when this is not going to...
Yeah, when does this not work? So I tried to give some of those caveats in there, but especially when you have... all of this basically assumes independent and identically distributed data, that sort of thing, where I gave the example before of... maybe a sneech is taking the test and they're not passing their notes off to the next sneech, right? The next data point does not depend on the original data point. In that case, if you start to do shuffling tricks, you'll end up with results that are completely off. So you have to be very careful about that, and sometimes that non-independence in your data can be really, really subtle. So I'd watch that talk by Chris Fonesbeck that I referenced for some of those situations. He has some great examples of things that have happened in the real world where these sorts of subtleties come up. The other thing is, if you have very, very few samples, if you have 3 samples and you start shuffling them, you're not going to get a very good proxy for your sampling distribution. And then there's some other more detailed considerations that you can look at in those books that I mentioned.
So is there anything, one of the implicit assumptions here is that when you're writing code like this is that the random number generator is actually a random number generator. Is
Yeah.
that, like, do you have any advice specifically about Python about, like, are there any caveats about the random number generator there? Any advice?
That's a great point. So this, like you said, this all depends on your random number generator actually being sort of random. And one thing about random number generators is almost none of them are actually random, right? They're all deterministic. Even the one, if you import the random module in Python, you give it a seed, and it creates a deterministic stream of random numbers. Now, those numbers have properties of randomness, and they sort of reflect what you would expect random numbers to look like. But this distinction of pseudo-random versus random is really subtle and really important here. So if you use a very unsophisticated random number generator, one with a very low mode or something, these sort of approaches can fail, and they can fail in ways that are hard to detect. But the good news for us in Python is that we have a built-in random number generator based on some pretty sophisticated methods. This same random number generator is also built into NumPy. And for all intents and purposes, you can treat the Python random module as producing real random numbers. But as hackers, you all know the difference between pseudo-random and random number generators. So you can keep that in mind as you're answering these sorts of questions.
Jake, thank you very much. Excellent presentation. I am also a budding statistician, and I know it's not the right Python function call. I think it's a gamut distribution. I'm not sure, but where you can
Which
say
distribution?
The gamut distribution, where you can specify the mean and the standard deviation of your sample set, and it can create however much you want. Is there a reason why you didn't use that for generating more sample data in your examples here?
Yeah. So I guess the question is, if you know your data is coming from a gamma distribution or a normal distribution, that's completely valid. But the normal distribution is only really, in most cases, is only really an approximation. So if you use, say, a normal distribution and you generate more data from that distribution, what you're learning about is the normal distribution that you've assumed fits your data. And what we want to do in these methods is we want to not make those assumptions about what the distribution is, but rather kind of let the data speak for themselves in terms of the distribution. And that's why we don't do these things. So it's a great solution if you actually know that your data is normally distributed with a certain mean and a certain standard deviation.
Thank you very much.
Yeah.
Just wanted to confirm on the example where you had the points plotted and then you split it into two graphs. Did you just randomly pick the values, like depending on which graph it was going to go on, they were randomly picked?
Yeah. So that's the key to this cross-validation is that it's a random split.
Okay.
Especially, you might have a data process that's kind of biased where the first half is slightly different than the second half. And then if you do a split down the middle, you would run into problems. So for packages like scikit-learn, they'll automatically do the right kind of random split to make sure that you're getting the right answer on your data.
Thank you.
Yep. Maybe one last question?
Sure. When you talk about cross-validation and it's not a good idea for smaller, like if you only have 20 points or something like that, what do you do when you have...
Yeah, that's a good question.
You don't have a ton of points, but you still don't want to overfit, or...
There are a couple things.
Even if you can just give me words, I can look up on the internet.
Yeah, there are a couple things you can do. So one, you could do something like a leave one out validation. So rather than splitting your data in two, you just hold out one data point and you fit it on the other 9, and then ask how well it fits out one. Okay. So that gets you a little closer to having the full data set. Yeah. But I think the broader answer is that if you're doing machine learning on 10 data points, you have bigger problems.
Sure. Okay. Thanks.
Well, let's all thank Jake for his great talk.